Today we'd like to take another step toward the birth of quantum physics, and we are getting very close to the beginning of the actual quantum. There's just a few more things you need to know. Let's start by recapping the important thing you need from the last lesson for this lesson, and that is an emission and an absorption spectrum. Emission spectrum comes from an object that is giving off light that is not getting hot. Think fluorescent bulb. Think a glow-in-the-dark object that is glowing and giving off light, but you can still touch it. Think glow stick. Think lightning bug. Okay, when you look at the spectrum coming off of these objects, the thing that struck scientists was that not every color of light was coming off. A few unique wavelengths came off, and that's it. Scientists did not understand why these wavelengths came off, but the others did not. They also did not understand how light could come off without the thing getting hot. With the absorption spectrum, you want to remember this is a hot object, a hot glowing object that's giving off light based on its temperature. It's giving off every single color of light. That light then passes through some sort of cloud of a certain material, and for some reason, certain wavelengths get removed from the spectrum. So this was our absorption spectrum, and again, scientists didn't understand why some wavelengths made it through the cloud and a few wavelengths did not. The first person to try to explain this was a guy named Niels Bohr. What Bohr did is he focused on the electrons in the atom. At this time, scientists weren't sure exactly how the electrons behaved in the atom. Where were they? What were they doing? Bohr looked at this and thought, maybe the electrons are in orbits, and these orbits are responsible for the light that is coming off of the atom. So this is what he proposed. He said the electrons can be in certain distinct orbits. All other possible orbits are forbidden. So the orbits can't just be any old place they want. They have to be in certain locations. And then what Bohr envisioned is that when an electron fell from a higher orbit to a lower orbit, light would come off of the atom. So light comes off of the atom when the electron falls from a higher level to a lower level. That light that comes off of the atom is determined by the spacing of the orbits. So in this case, there are 3 possible transitions. So that means there are 3 possible wavelengths that could come off of this atom. Since each element had a different configuration of possible orbits, reasoned Bohr, each element would have its own unique pattern of colors that came off. So the colors that come off are determined by the spacing of the orbits. That was what Bohr's proposal was. He proposed a theory for why some colors came off and others didn't. It had to do with the spacing of the orbits within the atoms of different elements. For the absorption spectrum, he envisioned the electrons at lower orbits being boosted to higher orbitals. Since there are only a set number of orbitals, only a set number of wavelengths could be absorbed, the ones with just enough energy to boost it to that other level. So Bohr set up a model that seemed to explain the emission and absorption spectrum with some sort of logic behind it. However, I want you to realize that Bohr's hypothesis was not immediately embraced by all scientists because some of the assumptions that underlie it did not really conform to the science of the day. So let's look in a little more detail. Okay, these are the 4 assumptions that Bohr came out with. Assumption number 1, he said, what holds the electron in orbit? Well, it's not gravity, which is the force that holds planets in orbits around stars. he said it was an electrical force, which is logical because the electrons are negative, the protons are positive. Gravity is way too weak to hold the electron in place, but the force electric is not. So he envisioned the force electric being the force that holds the electron in orbit around the atom. Remember that without this force, the electron would travel in a straight line, according to Newton. Objects in motion stay in motion at a constant speed in a constant direction unless acted upon by an outside force. So this is the outside force that keeps it in orbit around the atom. So this is assumption number 1, and this fit with classical physics, the physics that was around at the time of Bohr. Scientists can accept this assumption of the Bohr model. The second assumption is the one we already talked about. That is the assumption that electrons can transition between orbits or levels by absorbing or emitting energy. So an electron in a higher level can transition to a lower level and in the process give off light. This assumption explained beautifully the emission and absorption spectrums. Okay? It could fall to a lower level. It could emit energy in the form of light. It could absorb energy in the form of light and get boosted to a higher level. Again, this assumption, number 2, did a great job of explaining the two spectra that scientists did not understand. Realize the absorbing energy, it does not have to be light energy that is absorbed. For something like a glow-in-the-dark object, yes, it absorbs light energy and it boosts the electron to a higher level. And then when the electron falls back down again, it emits light. It glows in the dark. It's glowing not because of its temperature, but because of these excited electrons. Okay, but it can also absorb energy in the form of a chemical reaction. So like with a glow stick, you break the glow stick, a chemical reaction happens. Some of the energy causes the electrons to be in a higher energy state, and when they fall, they give off light. Same thing with lightning bugs and other bioluminescent creatures. With a fluorescent light, the energy is in the form of electrical energy, a voltage. A voltage boosts the electron to a higher level, and when it falls back down again, it gives off light. Okay, so the absorbing can be absorbing light. It could absorb electrical energy, voltage, or it could be a chemical reaction that is giving the energy to the electron. Okay, so that is assumption number 2. It's assumption number 3 that was a hard pill for scientists to swallow. Bohr said that electrons in stable orbits don't radiate. He said that because otherwise this whole model would fall apart. The problem is, this makes no sense according to classical physics. Here's the problem. Electrons that are orbiting are accelerating. By definition, they are changing direction. They are accelerating. We know that accelerating charges give off light. If it gives off light, it loses energy. If it loses energy, it should be constantly spiraling inward, and the electron will eventually, and by eventually I mean a few nanoseconds, it'll eventually collide with the nucleus and no longer exist as a separate, distinct particle. So the problem is with the Bohr model, without assumption 3, the electron cannot last in orbit. The orbits would be destroyed almost instantaneously. So he says this, but with zero justification for it. Okay? So it's a hard pill for scientists to swallow, but the model does such a great job of explaining the emission and absorption spectra that scientists want to find a reason why this can be true. All right? So keep your eye out. In the next few days, we'll figure out what was going on that made this statement true, even though it seems like it shouldn't be true. The final statement is one that I hope to explain to you now. When Bohr was setting up these orbits, he said some orbits are valid and some orbits are not. What makes one orbit valid and another not is this equation. Again, according to Bohr. So here's the equation. L. L stands for the angular momentum of the electron as it orbits. And according to Bohr, it had to equal n, which is an integer. N could be 1, 2, 3, 4, 5, or any integer. It can't be a decimal or a fraction. It's got to be a perfect integer. Times Planck's constant, which you can find on your reference sheet, divided by 2 pi. Again, he arbitrarily sets up this equation. But this equation is going to let him find the radius of his orbits, because angular momentum is equal to regular momentum times the radius of the circle. Okay, so this equation gave him a way to figure out the radius of each of the different orbits. All right? So the orbits are restricted to ones where the radius follows this equation. Again, there's no physical justification for why he would say that the angular momentum has to be an integer times this constant. We are going to find out why in just a few days, and it's pretty crazy. Again, Bohr has no idea why. Just a couple of words on orbits. This first orbit would be when n equals 1, and that orbit is called ground state. This orbit would be the second, where you plug 2 in for your n value, and that's called your first excited state. This orbit is n3, and that would be your second excited state. Eventually you'd reach a point where n equals infinity, and that means that the electron has actually left the atom and has become ionized. Okay, how good was the Bohr model? Well, when Bohr applied his 4 different premises to hydrogen, he got perfect agreement. So he took hydrogen, he used the formula for the angular momentum to find the different radii. He then used those radii to find the Coulomb force. He then used the Coulomb force to find acceleration. He then used acceleration to find the velocity of the electron, and then he worked out the details for the energy of the electron. He mapped out these energies and got values that look something like this. It turns out these had perfect agreement between these numbers and the actual light that came off of the hydrogen atom. So for instance, if an electron fell from n equals 3 to n equal 2, he could subtract these 2 energies to find the energy of the light. He would then put it into a formula that said the energy of light equals Planck's constant times frequency. He could then use his formula that said wavelength equals speed of light over frequency, and he could get the wavelength of the light, and it turned out that he would be able to predict exactly which wavelengths would come off. It worked beautiful. So even though some of these assumptions have no physical justification in his time, there seems to be something to this because it predicts the behavior of hydrogen perfectly. It did not work so well for other elements because of all the extra electrons. Some reason things became a little bit more complicated. Well, it turns out there's more going on than Bohr ever realized, and we'll talk about that later.